Okay, can you still see that, guys? It's just on, you'd only be able to see one slide at a time now, yeah?
Yeah.
Okay, fantastic. Right, so welcome to week 2 of Fundamentals of Chemistry. I hope I didn't put you off too much last week with all of the discussion about the atoms and electrons and all that stuff. We're going to build on that a little bit more this week, and we're going to look at the concepts of the chemical bonding. Okay, so what I mean by that is that we looked at the subatomic particles of an atom. So we have your protons, neutrons, and electrons. And we discussed how the electrons are within that kind of electron cloud around the nucleus of an atom. Okay, those electrons are the only subatomic particles that are involved in chemical bonding. All right, so we're going to touch on how those electrons actually bond to form different types of molecules, the types of bonding that they can be involved in. So we have ionic and covalent bonding. And then I'll talk to you a little bit how we represent that using some diagrams. Okay. So guys, just to double check, can you see the next slide that says the octet rule? So just on one screen?
No, it's still on the
First one.
the first one.
Okay, no worries at all. Just bear with me 2 seconds. Sometimes this happens. Okay, so you should be able to see that screen now?
Yeah, there we have it.
Yeah.
Yeah.
Okay, brilliant. So in our discussion last week on the periodic table of elements, okay, so I did mention that certain groups of elements differ in how stable they are and therefore how reactive they are. Okay. So I showed a video of a particular group 1 element. So how they donate an electron because they're incredibly reactive. They only have one electron on their outermost shell. They want to get rid of that electron and therefore it will react very, very quickly with other molecules. On the other side of the periodic table of elements, you have group 8 elements or noble gases, and they are incredibly stable. And the reason for that is because they have 8 electrons on their outermost shell. Okay. Where I'm going with this is that they satisfy what's called the octet rule. All right. So this is a driving force for all chemical bonding between different types of molecules in chemistry. Okay. So it's a simple rule of thumb. Okay. So it just states that atoms will combine in such a way that they have 8 electrons on their outermost shell. So basically what that's saying is all atoms are striving to have that stable outermost shell of 8 electrons. Okay. So they will combine in such a way to achieve that so that they can achieve that stability. All right. What I will mention here is that only electrons are involved in the bonding of 2 or more atoms to one another. Okay. So the protons and neutrons, they are in the nucleus of the atom. They do not participate in bonding. We're only looking at the electrons here. So what you need to know here is that all atoms are striving to have 8 electrons on their outermost shell, and that's what will drive how they interact with one another in order to achieve that. Okay? Okay, so looking at this and how it relates to the periodic table. All right, so this kind of ties into the groups that I mentioned previously. So all atoms, except of course the atoms that are in group 8, because they have already achieved the octet rule, they are satisfying the octet rule, they already have 8 electrons on their outermost shell. All other atoms, so from between groups 1 and 7, they will want to try and achieve the maximum number of electrons in the outer shell, which is 8. Okay? So in doing this, they have 2 choices. They can either lose the electrons, so they can donate those electrons to another molecule in order to get rid of them and achieve almost step back the way and get rid of their electrons in order to achieve a stable shell, or they will accept electrons. So they will take on additional electrons in order to satisfy that 8 electron rule. Okay. So in saying that, well, there's kind of a general grouping of these. Okay, so atoms that are in group 1 to 3, they tend to lose or donate their electrons when they react. Okay, so I've included a couple of examples here. So you'll see lithium. Lithium there has 1 electron on its outermost shell. All right. Actually, I won't use that as an example because that's a little bit of an exception. So we'll move on to magnesium here. So do you see the way it has 2 electrons on its outermost shell there? Magnesium, when it's involved in the bond, will donate those electrons in order to basically move back a shell and have that stable 8 electron shell on its second sublevel there. Okay, so those two electrons there, they will be donated in when it's involved in a bond, and doing so, it will achieve that 8 electron shell by giving those away. Okay, because you can see that stable 8 electron shell just beneath that shell there. Does everyone see that okay? Yeah. Perfect. Okay. So then looking, I suppose, at the atoms in group 5 to 7, okay? They will either accept or gain electrons when they react. Okay, so if we see oxygen there, oxygen on its outermost shell has 6 electrons. Okay, so we have two there, and then these two on either side. When oxygen reacts, it wants to take on an additional 2 electrons in order to satisfy the octet rule. The same for chlorine over here. So we have 2 electrons, 2 electrons, 2 electrons, and 1 electron, totaling 7. So in doing so during a bond, it will take on 1 electron in order to achieve that stable outer shell of 8 electrons. So once it bonds, it will gain the number of electrons that it needs in order to satisfy that 8 electron shell. Okay. Is everyone okay with that? Would you like me to go back over any part of that there?
What about atoms in group four? Will they
So
just go for whatever? Will they try and give or take or?
So I suppose for group four, that is a little bit of an exception to the rule that we're not going to cover because
Oh,
that
okay.
tends to go into it's half stability. Okay. So it's kind of that's more delving into the kind of transition metals and things like that because they act differently. So we're going to focus more so on groups 1 to 3 and groups 5 to 7.
Yeah, perfect. No
All
problem.
right.
Thanks.
Okay. So I suppose looking at different types of chemical bonds that we can have. Okay. So there are three main types. So we can have an ionic bond. So this is electrostatic interaction between ions of a metal. So that's maybe your group 1, and a non-metal, which would be your groups maybe 6 and 7. Okay. Your covalent then is the sharing of electrons between two non-metals. Okay, so ionic bonds will always involve a metal and a non-metal. Covalent will involve the sharing of electrons between two non-metals. So this will depend what group they're in. All right. We also do have metallic bonds. Okay, so this is taking metal atoms that are bonded to several other atoms. So this is including complexes that are made from your gold, copper, magnesium, and so on. But we're not going to touch on those. Okay, so I just wanted to highlight that there are three. We're going to focus primarily on our ionic and our covalent bonds. Okay, so starting with our ionic bonding. Okay, so the main thing you need to know here is that it occurs between a metal and a non-metal element, and it involves the transfer of electrons between the metal and the non-metal element. Okay. We'll touch on the difference between ionic and covalent a little bit later on, but all we need to know for now is that it involves the transfer of electrons. So in this case, okay, so think of it this way, we have a metal and a non-metal. One of those atoms of the elements are going to lose electrons. Okay. So they're going to lose an electron and become what's called a cation or a positive ion. Okay. Why does this happen? Okay, so if you think about it, if you were to look at the periodic table of elements, if one of those atoms were to lose an electron, it now has one more positive charge from the protons in the nucleus than it does electrons. Okay, on the periodic table of elements, they're all neutral. If a bond starts to occur between one element and another element, we essentially give away an electron. Okay. So once we did have kind of that equality between our positive and our negative charges, protons in the nucleus, electrons on the shell, if we give away one or more electrons, it's going to have an imbalance. So there's going to be more positive charges than there is negative charges on that atom now. And that becomes a cation or a positive ion, we call it. Okay. In the same breath, then, the atom that gains the electron, so once that transfer of electron happens, and the atom that gains the electron, that will become what's called an anion or a negative ion. So that is taken on basically more negative charge because it's accepted another electron. it now has that imbalance of negative charge from the electron in comparison to its protons in the nucleus, and now it adopts an overall negative charge. Okay? So essentially what that boils down to is that an ionic bond is formed between the electrostatic attraction between a positive and a negative ion. Okay, so think of it like opposites attract, like repels. All right. Does anyone have any questions on that so far? So everyone can see where the difference in the charges are coming from. So we did start with neutral atoms, and now based on that kind of transfer in electrons, we have an imbalance. Okay, so one is going to become more positive, one is going to become more negative. So how we actually represent these diagrams, okay? So as scientists, we can actually predict how certain molecules are going to bond together, and we can use kind of simple enough structures called Lewis dot structures. So we basically, and I'll do a couple of examples of these, that we draw the structure of the element. We use electrons as simple little dots around the symbol of the element, and we can use that to predict will certain atoms, when they bond, will they form a stable molecule? So A, will they satisfy that octet rule? And what will that molecule look like? So it's almost like a predictive, a kind of a first pass predictive prediction on what that element is or that molecule is actually going to look like. So it's almost we use an awful, or modern chemists, they also use an awful lot of kind of advanced bonding theories to predict molecular properties and so on. But the Lewis dot structures are almost like the first chance at that. So we look and we see how we can predict what that molecule is going to look like. And I'll show you an example of that, what that actually looks like here. Okay. So say if I were to take oxygen, okay, so just a little bit of a recap from last week. Oxygen has an atomic number of 8, which means it has 8 protons in its nucleus. We're just going to deal with it as a neutral atom at the moment. So that means the number of electrons it has is also 8. Okay, so there's no additional charge here. We have 8 protons, 8 electrons. Those charges cancel each other out. It's a neutral atom. All right. The atomic mass number then from here is 16. Okay, so we round up to the nearest whole number. We have 16 as our atomic mass number, which means if I wanted to work out the number of neutrons, just as a bit of a recap, I take away the atomic number from the mass number to give me a total number of 8 neutrons. Okay? It's not really relevant for the valence or the dots diagram. I just wanted to kind of give a little bit of a recap there. So if I were to look then at the electronic configuration of oxygen, okay, so looking at this, I have 8 electrons to fill in. So as a recap of last week, okay, so on the first energy level that surrounds an atom, you can hold 2 electrons, okay? So if I were to draw 2 shells around oxygen here, the first one would only have 2 electrons on it. The second one then, so I have 6 in total to fill in once I take away those 2 electrons, and that's what I represent on the Lewis structure. So there's your 6 remaining electrons. For Lewis structures, we don't take into account the previous energy levels. Okay, so we're only dealing with that outermost shell. Okay, so if you were to draw oxygen there, we only represent the 6 dots that are the valence electrons or the electrons on the outermost shell. Okay, is everyone following me there? All good? Okay, perfect. So valence electrons on the outermost shell, we're only dealing with those. So the Lewis structure for oxygen would be our symbol for oxygen there plus our 6 valence electrons. So just showing you a little bit of a couple more examples then. So if I were to show you across period 2 of the periodic table, so we have our lithium, beryllium, our boron, carbon, nitrogen, oxygen, fluorine, and neon. You can see there that the outermost or the valence electrons increases across the period. Okay. So it allows us to see easily the number of valence electrons that we have in an atom. Okay. So if I were to show you, that's across the way, so that's across the period. Group 1 will always have one electron on its outermost shell. Group 2 will always have two electrons on their outermost shell, and so on. So this is just showing you across the period. So atoms with 8 valence electrons, they're particularly stable, so they don't really participate in bonding because they don't have to. They don't have to satisfy that octet rule. And they're easily identified because they have 8 dots. So neon there is an example of that. Neon doesn't have to react in order to gain stability. It's pretty much happy and stable on its own. And we can see that then from counting the 8 valence electrons that are around its shell. Okay. We do have one exception because, of course, all chemistry involves exceptions here, there, and everywhere. But we have helium. Okay, so that's our second element on the periodic table. And this consists of 2 dots, so two paired dots called a duet. So, like I said, the first energy level can only hold 2 electrons, okay? And then after that, the second energy level can hold 8, the third energy level can hold 18, and so on. What we're looking at here, helium, it's our second element, that already has 2 electrons on its outermost shell, which is the first energy level. All right. So that's particularly stable on its own because that first energy level is considered full. I know it's not 8 electrons, but the first energy level can only hold 2. So therefore, it's at max already. It does not need to undergo bonding in order to gain stability. Okay, so that's just one exception to the rule there. Okay, so we have an examples of a couple of ionic bonding, okay, using that Lewis structure here. So the first one is salt, okay, so it's our sodium chloride, and I'll show you where this comes from here. So hopefully. Okay, so everyone can see there. So sodium, okay, so sodium is a group 1 element, okay, so it has one electron or valence electron on its outermost shell, and that typically combines with chlorine to form sodium chloride or a salt, okay. Chlorine is part of group 7, so it has 7 electrons on its outermost shell. So what will basically happen is that sodium wants to get rid of that electron. Okay, it's not stable having that one electron on its outermost shell, so it essentially wants to donate it as quick as possible. In doing so, it forms that cation I was talking about. Okay, so it donates the electron towards chlorine and then does form an 8. So it gains stability because it goes back an energy level that has a full 8 electron shell. All right. It gains that positive charge based on what I was talking about. All right. So because it now has one less electron than it does protons, the protons are now predominating. They have a positive charge. So it's a positive charged ion now. Chlorine, then, on the other hand, like I said, it's group 7 and has 7 electrons. To gain stability, it wants to accept another proton, or sorry, accept another electron from something. It accepts it from sodium, gains that 8 electron shell, and because now it has one more electron than it did at the start, it's now negatively charged. Okay, so there's one more electron than there is protons. Can everyone see where that's coming from, yeah? Okay, so sodium is now stable. It's gotten rid of that valence electron. Chlorine now is now stable because it has gained that electron and has completed the octet rule. So I'm just going to try something here just to see if I can bring up the whiteboard. Just bear with me 2 seconds here. Okay, perfect. So I just want to do a couple of these examples just out on a whiteboard. So I just wanted to be able to see it. So I'm going to do, if you have the notes in front of you, I'm going to do the magnesium oxide example. Okay, so just very quickly then. So we have magnesium on one side, and then we have, oh, okay, so we have magnesium and oxygen. Okay, so these combine to form magnesium oxide, and I'll show you how we do that then based on our Lewis structures. All right, so if we were to look at magnesium on the periodic table, it has 2 electrons on its valence shell. Okay, so it's 2 valence electrons that are available to bond. Okay, so what will happen here? Magnesium, because it's in group 2, will want to donate these to another element as quickly as possible in order to gain that stability and its stable octet shell. Oxygen then has our 6 electrons on its valence shell, and it's missing 2. Okay? So essentially, oxygen is in group 6. It will want to take 2 electrons from one other element in order to satisfy its octet rule. So what that will look like then, so if I just were to come over here, okay, so we'll have magnesium once it reacts with oxygen, and we'll also have our oxygen over here. So essentially, like I said, magnesium will get rid of those 2 electrons. Okay, so sorry, I can't do a superscript on this, but it's given away those 2 electrons. Okay, so it's donated those electrons to oxygen. It now has 2 more protons than it does electrons in its nucleus, and it has a 2 plus charge. Okay, so it has 2 more protons than it does electrons. Looking at oxygen then, so what changed here is that it kept its 6 electrons that it started with. Let's put these in a different color. And it accepted those 2 electrons from magnesium. Okay, so these were essentially donated, these 2 here. Magnesium donated those 2 electrons to oxygen. Magnesium became positively charged by 2 because it gave away 2 electrons. These 2 electrons were donated to oxygen, and oxygen developed a 2 minus charge. Okay, because it took on 2 more electrons than it does have protons in its nucleus. So we'll just call this over here 2 minus. All right, so you would represent this as a superscript above it, but just for now, we'll just write it next to it. Is everyone happy enough for that, where that's coming from? Okay, so I won't do, will I go through the second example just so you can see it, or are you happy enough to move on? I'll just go through the second example that we have just to finish that off, okay? So if you're looking at the notes then, so we have calcium, and we also have 2 chlorines. Okay, so ionic bonding can happen. I suppose this is a good example as well because it shows that ionic bonding can happen between 2 or more elements as well. It's not always as simple as just having 2 elements that combine. Okay, so in this case, then we have calcium and we have 2 chlorine atoms. Okay, so in the same way as our calcium or our magnesium, sorry, we have 2 electrons on the outermost shell, or valence electrons for calcium. All right. For our chlorine then, so that's a group 7 element. Okay, so we have 7 electrons on its outermost shell, so it looks something like this. Okay, so calcium in this case is going to donate 1 electron each to these chlorines. All right, so we have one valence electron that's going to be donated to this chlorine atom, and 1 valence electron that's going to be donated to this chlorine atom. So it shows, I suppose, that like ionic bonding, it can happen between 2 or more atoms. All right. In the exact same way then that we had up above, so we have calcium, that's after donating 2 of its valence electrons. So that will gain an overall 2 plus positive charge. All right. 2 more protons than it has electrons. Our chlorines then, so we have 2 of these here. Okay, so in the exact same way as above, it kept its valence electrons that it already had. Okay, so that's our 7, 2, 3, 4, 5, 6, 7. And then it gained 1 valence electron each from our calcium, and as such developed 1 minus charge for each one. So what you might see that written as, and I'll do it for magnesium as well, is you'll see that written as CaCl2. So that 2 is a subscript. But if you saw calcium chloride on the shelf and you were to pick it up, that's the empirical formula that you would see. The same way for your magnesium. Oh, sorry. So you would see an empirical formula that looks something like this for your magnesium oxide. Okay, so that's where that 2 comes from. It represents the 2 atoms of chlorine are involved in the ionic bond with calcium. Is everyone happy enough with that? All good? Okay, perfect. So I'm going to close that down just for the time being, and then I'll switch back over to the notes. Okay, everyone can see the notes okay now, yeah? Perfect. Okay, so not to confuse it too much, okay, so we've talked about Lewis structures, okay, so they're the simplest diagram that we can use to predict the ionic bond between, or ionic or covalent bond between our 2 or more atoms of elements, okay? We can also use a Bohr diagram. So Bohr diagrams are much more detailed, okay, so they show the complete arrangement of electrons that surround the nucleus of an atom. So as you can see, when I was drawing with Na or sodium originally, if I was using a Lewis structure, I'd only show this outermost electron here. Okay, so I'd only show that shell. What the Bohr diagram takes into account is the complete arrangement of electrons. So it shows me the first energy level containing 2 electrons, my second energy level containing 8, and then finally then my third energy level that contains 1. For my chlorine then, it shows the exact same thing. My first energy level that's full, second energy level that's full, and then my incomplete third energy level there. So I suppose you can do it either way. It represents the same thing. The Lewis diagrams are a little bit more simpler because they only show that valence cell or our valence electron. So guys, what I'm going to do now, just to give you a break between the 2 different types of bonding, I suppose, that we're going to talk about, I'll give you maybe a 10-15 minute break now. When we come back after the break, I'll go into the covalent bonding and show you the difference between obviously what we talked about with ionic bonding versus covalent. And then we might do a couple of example questions towards the end of the session then. Is that okay?
Yep.
Yeah.
Okay, brilliant stuff. So if we're all back here by about 6 o'clock, that should be plenty of time.
Yeah.
Okay, brilliant. So we discussed ionic bonding then before the break. So as I said, there's 3 different types of bonding. All right, so ionic, we have covalent, and we have metallic. Okay, so we're only going to focus on ionic and covalent. And here's where the difference between ionic and covalent happens. So ionic bonding is the transfer of electrons from one element to another element. Okay, so we saw that with a couple of examples that the valence electrons will be transferred to another atom of an element in order to satisfy that octet rule. For covalent bonds, these occur typically between 2 nonmetals. Okay, so while ionic bonding was between a metal atom and a nonmetal atom, covalent bonding typically occurs between 2 nonmetal atoms of an element. And in these, they share the electrons. Okay, so there's no official transfer of an electron from one to the other. They share them between themselves. So the atoms that can be shared are the valence electrons. Okay, so these are still the electrons on the outermost shell. They're just not transferred from one to the other. They're shared amongst them. But we can also use the Lewis or the Bohr diagrams to represent this covalent bonding. Okay, so you'll see this in fluorine. Okay, so fluorine naturally exists as F2 because of its instability as one atom. Okay, so fluorine is a group 7 element. Okay, so you'll see it there. It has 7 electrons on its outermost shell. And it doesn't want to exist on its own. All right, it's not stable enough to exist on its own as so. So it will want to combine with a second fluorine atom in order to satisfy its octet rule. Okay, so you'll have 2 group two group 7 fluorine elements coming together. They will share these two electrons amongst themselves, okay? So that each fluorine atom exists with a stable octet shell. All right, so it's these two electrons I'm focusing on here. And then they will be shared amongst two fluorine atoms in order to satisfy that octet rule. So we'll see a couple of examples here. So I'll pull up the whiteboard again and we'll do two examples of them. But you can see it here with the structure of water, okay? So oxygen has six, like we said, it's 6 valence electrons on its outermost shell. Okay, it's a group 6 element. That will readily combine with two hydrogen atoms. Okay, so hydrogen by nature has 1 valence electron to give, but they will share that amongst themselves. So oxygen basically has 2 electrons here that can be shared with 2 hydrogen atoms. Hydrogen then gets that exception to the rule with the 2 electrons on its outermost shell and it's stable. Oxygen will share the electrons that hydrogen has in order to satisfy its octet rule to give us this overall structure. Okay, we won't worry about these representing the bonds like this yet. Okay, we'll just focus on sharing those 2 electrons to form that structure. Okay, can everyone see where that's coming from? Yeah?
Mhm.
Perfect. Okay, so what I'm going to do, I'm going to just take our ammonia example there. I'll stop sharing the screen and I'll move back onto the whiteboard. Okay, everyone can see the whiteboard okay now, yeah?
Yeah.
Okay, perfect. So in this example, if you're following along on the notes, okay, so I have nitrogen and I have 3 hydrogen atoms available to bond with it. Okay, so nitrogen is a group 5 element, okay, so it means it has 5 electrons on its outermost shell. And then as we just had, hydrogen has 1 valence electron on its outermost shell. Okay, so 1 electron each on their outermost shell. So to satisfy the octet rule for hydrogen, so to give it that exception to the rule of 2 electrons on its outermost shell, it will want to combine with the electrons on nitrogen, okay? Similarly then, to get a stable octet shell of its own, nitrogen will want to share these electrons 1, 2, and 3 from our hydrogen. So in the course of what happens there, so we have nitrogen there that will, oh, okay, so let me just change this over. Okay, so nitrogen still has its 5 valence electrons that it had itself. Then each hydrogen then will share 1 electron with it. Okay, so we'll just copy these over so we can see it. Okay, so each one of these hydrogens then will donate, or not donate, it will share 1 electron with that nitrogen atom. So if I were to draw its outermost shell, apologies for the terrible drawing. It would look something like this. Okay, so the electrons are shared on the outermost shells of each one of these. So those 2 electrons are being shared with this hydrogen and nitrogen. Those 2 electrons are being shared with this hydrogen and nitrogen. And those 2 electrons are being shared with this hydrogen and nitrogen atom. So each one of those atoms of the elements have a stable octet shell without that transfer of electrons. Okay? Does anyone have any questions on that so far? Okay, so you can see it there. We have 8 electrons in play, but they're just being shared amongst those atoms of the element. All right. Will I do out the second example just so you can see it, or are you happy enough that you can see where it's coming from? Happy
We
enough
do
to
the second example.
Oh yeah, of course, not a problem at all.
Thanks.
Okay, so for the second example then, so I have our carbon in the middle, and then I have four hydrogens available for bonding. Okay. Okay, so similar to what we had before, so carbon has 4 valence electrons on its outermost shell. And then again, so hydrogen has 1 valence electron each. All right. So these electrons can be shared to satisfy the octet rule for each of these elements. Okay. So once they are shared, it would look something like this. So carbon will still be in the center. So carbon will still have its valence electrons it started out with. But now each of these hydrogens can contribute its electron to satisfy the octet rule. Okay, so we'll have 1 hydrogen there. Sorry, I'm just going to copy and paste these just to get a little bit quicker. Okay, sorry, just 2 seconds now. Okay, so each one of these hydrogens will contribute 1 electron each to give it 4 electrons that are being shared. And then our carbon already has the 4 electrons that it started out with. Okay? So those hydrogens will essentially come together with the carbon. They will share 1 electron each in order to satisfy the octet rule for carbon. So now carbon, once they're shared, has 8 electrons on its outermost shell. Hydrogen is then satisfied because it has 2 electrons on its outermost shell, which is the first energy level that it has. So it can only hold 2 electrons each. Is that okay? Everyone can see where that's coming from? Okay, perfect. So what I'll do is I'll stop sharing this. I'll switch back over to the notes. Okay. So again, we can have Bohr diagrams. Okay, so I won't complete these 2 examples in class because they're the very, very same. Okay, so I'll talk you through the hydrogen atom. So this is what we had already. Hydrogen can't exist as on its own. So it can't exist just as H. It exists naturally as H2 for the simple reason that it only possesses 1 valence electron each. So it only possesses 1 electron anyway, but it only has 1 valence electron. That's very unstable, okay? So it makes hydrogen quite reactive. So in order to regain stability, they will share 2 electrons amongst themselves, become H2, and that satisfies the octet rule for each one of those. Looking at, so I'll just talk through it maybe. So looking at fluorine. Fluorine is group 7. So we already had this in the previous slide, but you'll see it here that it has our 7 electrons on its outermost shell. Again, not as stable as it would like to be. It will exist primarily as F2, and it will share that electron that it needs between the 2 of them. Okay, so it will satisfy each one of their octet rules. Okay. Again, we see kind of a variation of this then with 2 oxygen atoms. All right, so carbon exists with, like we just had in our example, so it has four valence electrons, so you can see them there, 1, 2, 3, and 4. Oxygen has 6 electrons on its valence shell. It needs two, so it will basically share, it will share two of its electrons with carbon, and carbon will share 2 electrons back. But it needs two of those to combine. Okay, so that will happen twice. So you see it there. The valence electrons of carbon will combine with the valence electrons of oxygen in order to satisfy that octet rule, but it needs a second oxygen atom to allow that to happen. All right. So if we just focus on the carbon there, that now has 8 electrons being shared, and our oxygen then also has 8 electrons with the two from our carbons either side. And that's actually forms carbon dioxide. Okay. Can everyone see where that's coming from? Yeah. Perfect. So you see the
Sorry,
difference.
sorry, Saoirse, could you just explain the hydrogen atoms? I'm at a bit of a loss how that satisfies the octet rule. I must be missing something simple.
Oh, up here, yeah, of course, no worries. Okay, so hydrogen is our first element on the periodic table. Okay, so what that means is it basically only has one energy level. So the only exceptions, I suppose, to the octet rule are hydrogen and our helium. Okay, because they only have the first energy level. They don't have any more electrons to going to move up to the second and the third energy level. So the maximum that the first energy level can hold in terms of electrons is 2. So I suppose its octet rule is basically the duet rule. That can only hold
Oh,
two
okay.
electrons. So because they only have one each, they won't exist naturally like this because it's too reactive. So they'll combine to gain stability to satisfy having 2 electrons rather than 8.
Okay.
Does
Yeah,
does that
that
answer your
makes sense.
question?
It does, thanks.
Perfect, no worries. Okay, guys, so I'll keep moving on. So we'll talk about maybe just comparing our ionic and covalent bonding materials, okay? So they're largely different in their kind of physical and chemical properties, and this is what we talked about a little bit last week. So ionic compounds, they tend to be a lot more rigid. Okay, so they have strong electrostatic forces between them. So we saw that between our positive and negative charge. That is incredibly hard to break through a reaction. Okay. They tend to exist primarily as solids, so they have that kind of nice, very ordered crystalline lattice. Perfect example of that is salt. Okay, so if you were to pick up a flake of salt, you can nearly see that crystalline lattice pattern in a flake of salt. Okay, the ions arrange themselves like that, A, for stability, and B, because the electrostatic forces arrange themselves that way. Our covalent compounds, on the other hand, they're kind of separate molecules. So although they are sharing electrons, they're not as permanently bonded. I won't say permanently either, but they're not as strongly bonded as the ionic compounds would be. There's not that force of attraction between them, between the electrostatic charges, so it won't take much to break them apart. And this is what we'll see when we start looking at the chemical reactions. A lot of covalent bonds are quite easy to break. Because of this, then they usually exist as liquids and gases at room temperature. So our ionic compounds are normally the solids with that really nice crystalline lattice. Your covalent compounds tend to exist more as liquids and gases because they have very, very weak attractive forces between them. Looking at that then, our ionic compounds, okay, these tend to have very large melting points and boiling points. The reason for this is because of that really strong force of attraction, it requires a lot of thermal energy in order to break them apart. Okay, so we need to apply a lot of temperature, a lot of heat, and maybe sometimes a lot of pressure in order to break those bonds apart because that electrostatic force is so strong. On the other hand, covalent compounds, because we have very little attractive forces between them, it doesn't require as much energy as it would to break apart an ionic compound, and they tend to have very low boiling points. All right. Ionic compounds then they're usually soluble in water. Okay, so I won't go too much into this now, but just for now, we'll just talk about a little bit of solubility. The ionic compounds, once they're placed in water, they disassociate. Okay. We'll touch on that a little bit more when we talk about the actual specific reactions that they're in, but just for now, they're usually soluble in water because they can dissociate. Covalent compounds, they don't tend to be as soluble in water. All right. And for this reason as well, is that ionic compounds, they tend to conduct electricity. All right. If you look at an ionic compound, it's made up of electrostatically charged compounds. Okay, so think about your NaCl and that bonding I was showing you earlier. Na exists as Na plus. Your chlorine in NaCl exists as Cl minus. Because they have that electrostatic charge, they are able to conduct electricity in the liquid state. So they can physically carry an electrical current through a solution. Pure covalent compounds, they don't have that ability, okay, because they don't have that difference in charge. There's no transfer of electrons. They're sharing the electrons. That means there's not that imbalance between protons and electrons in their atoms. So they don't have a charge. They can't conduct electricity. All right, so it's just, we'll talk about a little bit more of that as the semester goes on, but just so you know the difference between them now. Okay, so covalent bonding then. So they don't have, how should I say, they don't have a formal electrostatic charge, okay? So again, think back to what I was talking about, that NaCl. Once that donates an electron, once sodium donates an electron, and once chlorine accepts it, there's a formal charge put on both of those. So Na becomes Na plus, chlorine becomes Cl minus. There's a physical transfer of an electron. Covalent bonding, they're sharing, okay? So there's not that transfer, there's no formal charge on these atoms, but we do have a couple of electrostatic interactions at play here. And we'll look at each one of these, okay? So we have the attractions between the electrons and the positive nuclei, okay? Electrons by nature are negatively charged. Your nucleus by nature is positively charged because all the protons are sitting in the nucleus of an atom. So you will have attractive forces between those. You also have repulsion between neighboring electrons. Okay, so if you bring two elements together, they each respectively have electrons, but they will start to repel each other. Okay, so just think about that, like repels like, opposites attract. If you bring two electrons close to each other from two neighboring atoms, they will tend to repel each other. It's like a magnet. But you'll also have that repulsion between their nuclei as well. So that positive charge will repel the positive charge on the second atom, and it won't allow them to come as close together. So I suppose where this all comes from is which one is the predominant force here? Which one allows those atoms to come together? Or are they just too positive or too negative, and will the bonding not occur because those repulsions are so strong? All right. Is everyone following along with that? Just so it's not a formal charge, but you do have certain electrostatic interaction at play. Is everyone happy enough with that? Okay, perfect. So I suppose the main thing to focus on here is that opposites attract, similarities repel. So that's going to be the case for all covalent bonding going forward. Okay, so this is where it kind of comes into play a little bit. All right, so we'll talk about this fluorine molecule here. Okay, so we had this example earlier, our F2. We saw that that shared electrons equally. All right. Fluorine atoms, the fluorine atoms are equal. Okay, so they both have 7 electrons. They're the exact same atom. They will come together and share that electron equally. They have equal affinity for that electron. So it's basically one fluorine is not pulling the electron closer to each other over the other. They have equal opportunity to share that electron. In the case of a molecule like hydrogen fluoride, okay, so our HF, you see this change in what's called electron density, all right? So think about F2, it's nice, it's shared equally. That electron is being passed equally around that molecule. In this case, the electrons are pulled harder towards fluorine, all right? So if you can imagine the fluorine is on this side of the molecule, our hydrogen is on this side of the molecule. The electrons that are floating around in this bond between hydrogen and fluorine, Fluorine wants to attract them more to itself. All right. It's more comfortable having a negative charge than hydrogen is. So it wants to pull all those electrons toward itself. So what will happen is the electrons will start to almost accumulate on this side of the molecule. Only for a split second, because they're continuously circling this molecule. But sometimes the fluorine will pull harder on the electrons. So it wants to almost hog the electrons towards itself, adapt a little bit more of a negative charge in hydrogen, and in doing so, pulls the negativity away from hydrogen, giving this a slightly positive charge. All right. What you need to know here is that fluorine, some elements are more comfortable having a slightly negative charge. And I'll talk about why in a second. Hydrogen is not one of those elements, okay? So that will want to adopt a slightly more positive charge, and that's called the sigma positive or sigma negative. All right? It's represented by that delta sign. But all you need to know at the moment is that certain elements will pull electrons toward itself because they're more stable when they have a negative charge, whereas some elements will want that electrons pulled away from them so that they can adapt a slightly more positive charge. And I'll discuss. So I suppose, why is this the case? And it's about this electronegativity value. All right, so this is our periodic table of elements, but certain elements have an affinity for electrons. Okay, so they have an affinity for adapting a slightly negative charge. Okay, they want a slightly negative charge. So certain elements will pull electrons towards themselves so that the other element in the bond can adapt a slightly more positive charge whilst they're comfortable having a slightly negative charge. So how this actually comes into play then with the trends in the periodic table. All right. So I have put up on Moodle a version of the periodic table that shows electronegativity values. But what you will notice is that the electronegativity value increases from left to right. Okay, so across a period. The reason for this, okay, is that just think about electronegativity as the atoms want to pull electrons towards itself. All right. So the reason it increases from left to right is that the number of protons, the atoms are getting bigger. All right. The number of protons increases across a period. It's getting bigger. It has more protons, more electrons. What that means is that there's basically more protons available to attract those electrons towards itself. So think about it this way, in that nucleus, the more protons you have, the more pulling power they have on that increased number of electrons to pull it towards itself. So because there's more, the electrons are going to be pulled closer to that nucleus, and you're going to basically decrease the distance between your proton that's sitting in the middle and your electrons. So because they have more force of attraction, they're going to basically be pulled towards that nucleus. All right. The best way I can describe it is think of a magnet. Okay, so if I had 10, in comparison, say if I had one magnet and one magnet, if I had 10 magnets and 10 magnets, they would draw more towards itself and they would decrease that distance. Okay? Everyone okay with that? You can see where I'm getting that from. Is there any bit on that you want me to go back over? Happy enough so far, yeah? Okay, perfect. So I'll talk about then what happens when we go down a group, okay? So increases across the period or from left to right, if we were to look at the periodic table of elements from decreasing, so from top to bottom, it decreases. And it's basically, if you would think of like a physical barrier, all right? So atomic radius increases down a group, so the atoms themselves are getting much bigger, okay? So as you can see, a lot of electron shells are being added as you go down a group. All right. So they do increase from left to right, but they're also increasing in size from top to bottom. Okay, so you're going to have more electron shells. For example, if you went from hydrogen that has one electron shell down to sodium, which has three, you can see that the atoms are physically getting bigger. All right. These electron shells, they basically behave as a barrier. Okay, so the nucleus is then surrounded by increased number of shells. They form a barrier between that force of attraction between your nucleus and your valence electron. Okay. Basically, what happens then is that they shield the attractive force between the nucleus and the valence electron, and the electrons on the outermost shell are not pulled as tightly, so they can be involved and be donated or shared easier than they could if they were drawn closer to the nucleus. All right? They don't feel that attractive power as much, therefore, they're available and more readily given away than they would if they were drawn closer to that nucleus. All right? So I won't go too much more into that, but it's just to note, and it's kind of just tying into what we talked about there, is that covalent bonds, they share electrons by nature, but it's not always shared equally. And the reason it's not shared equally is because of this electronegativity difference. All right. Is everyone happy enough with that so far? I'm not confusing you too much. Within reason, anyway. Okay, fair enough. Okay, so I'll talk, this is kind of talking a little bit more where that electronegativity comes in. All right. So we have what's called polar covalent bonds. So if I were to just, sorry, now skip on back here to F2. Okay, so like I said, these are being shared equally. Fluorine has the same affinity for those electrons. It doesn't want to pull it towards itself any more than the other fluorine atom does. So they're shared equally. This is called a non-polar covalent bond. All right, so basically shared equally, it's non-polar. What happens though when you do have a difference in electronegativity, so I'll bring back my hydrogen fluoride example here. Like I said, the fluorine is much more electronegative than hydrogen, okay? Your fluorine wants to draw electrons towards itself, whereas hydrogen is not as electronegative as fluorine, so it's kind of happy enough to adopt a partial positive charge, while fluorine adopts that partial negative charge. So what happens here is we have a slightly positive charge on one end, a slightly negative charge on one end of the molecule, and we create what's called a dipole. Okay? So the dipole is produced by two equal and opposite charges separated by a distance. Okay, so we're not going to go into this too much, but it's just showing you that on one end of the molecule we have slightly positive charge. On the other side of the molecule we have an equal but opposite charge, so we have negative charge, and they're separated by a certain distance. All right. So basically, the greater the difference in the electronegativity, the more polar the bond is. Okay, so we'll see a little bit what I mean by that in a second. So for example, okay, hydrogen fluoride. Okay, so we have a bond length of 0.92. The difference in electronegativity between hydrogen and fluorine is 1.9. All right. So that's incredibly, that has a huge dipole moment in here in comparison to the others. All right. HCl then, so our hydrogen chloride, has electronegativity difference of 0.9. Okay, so fluorine wants to attract the electrons towards itself an awful lot more than chlorine does. So the electrons are almost shared, are more equally shared here than they would be in hydrogen fluoride. Hydrogen bromide then, so again, it's a little bit less electronegative than chlorine. It doesn't want to share, it doesn't want to pull those electrons towards itself. They're shared a little bit more equally again. All right. So where this actually comes in to play, all right, is that you're looking at the electronegativity differences here. So we're looking at certain molecules, okay, and we'll do a couple of examples now in a second. But all you have to know here is that if the electronegativity difference is below 0.4, you can consider that a non-polar covalent bond. So, for example, our fluorine that almost had equal share in those electrons, that would have an electronegativity difference of below 0.4. Your polar covalent, so that's somewhere between say your hydrogen fluoride, your hydrogen chloride, so on. So just back on these. So say from hydrogen bromide up, they would be considered polar covalent because they're between the 0.4 and 1.8. All right. Anything above 1.8 is considered an ionic bond because the electronegativity difference is so strong between the two elements that are involved. And again, we tie into how strong that force of attraction is, and that's why we need increased boiling points and so on. So what I'll do is just to break it up a little bit, I'll just stop sharing the screen now. I'll go over to the whiteboard and we'll do a couple of these examples just so you can see where it comes into practice. So just bear with me 2 seconds now.
Hi, Saoirse.
Yeah, you okay?
Apologies, I'm going to have to get back to work now, but I'll catch up on the rest of the lecture during the week. Is that okay?
Perfect, not a problem.
Thank
See you
you.
then.
Bye-bye.
Okay, so we'll do hydrogen chloride as an example. All right. Sorry, just bear with me 2 seconds. Okay, so it would be if you could see the electronegativity table that I posted on Moodle, that would be great, just so you can see where these values are coming from. But if not, you can just search it on Google as well. All right. So basically, it's a version of the periodic table that just has its electronegativity values on it. I'll go through the examples now, but it is on Moodle in case you need to have a look at it. So if I were to look at those tables, okay, so hydrogen by nature, okay, has an electronegativity value of 2.1. So these are all given values, all right? Chlorine then by nature has an electronegativity of 3. So how you would determine the bonding, okay, using these electronegativity values is that you take the electronegativity differences away from each other. Okay, so these are the electronegativity values of the respective elements. If I wanted to work out the electronegativity value of the entire molecule, I would just take one from the other. So that would give me 0.9. Oh, sorry, I don't know what I did there. Okay, so that would be 2.1. So that would give me 0.9 in total. So then going back to the differences in electronegativity there, because that is between our 0.4 and our 1.8, that would mean I have a polar covalent bond. Okay, and it's all to do with the differences in electronegativity there.
Sorry, those aren't the numbers on the periodic table that you linked, unless I'm reading it wrong. It's saying hydrogen is 2.2 and chlorine is 3.16. Unless,
Oh,
and
okay.
I could be reading it wrong.
So it is common that some of them they may kind of have the more accurate
Oh yeah,
electronegativity
okay.
values. Um, you will be given that in the exam anyway, so you won't have to learn off the
Okay,
electronegativity values.
perfect. That's yeah, okay, cool. Thanks.
Um, so we'll just if you want to call it just so we kind of have all of the same thing. So it was 3.16 and it was 2.2, was it?
Yeah.
Brilliant. Okay. Yeah, some of them just have the kind of more accurate value, but we'll go with it anyway. Yeah, so that will kind of give us 0.96. Yeah, which still gives us the polar
Yeah,
covalence.
perfect.
All right. Um, so for example, then let me just see. We'll do the NaCl version because that's going to give us our ionic. So NaCl. So yeah, so I just pulled up one in front of me, but I'll just go with the values I have, but you can sub in the ones that you guys have on Moodle, all right? So in front of me then, so NaCl, or Na, sorry, has an electronegativity value of 0.9. Our chlorine then is our 3.16 just from above. So again, if I want to work out the electronegativity value, I would take that 0.9 away from 3.16. So that should give me 2.26 based on these figures. And because that is well over the 1.8 cutoff for ionic bonds, I now know that they form an ionic bond. Is everyone happy enough where that's coming from?
Yeah.
Perfect. Okay. So I don't want to confuse you too much with kind of trends in electronegativity and so on. I just want to show you kind of where those differences come from. So you'll see it actually on that table that you have in front of you, that it will increase going across a period and will decrease going down a group for the reasons I went through. But the main reason we're using electronegativity is to predict what type of bond that we have. All right. So there's going to be a couple of examples like this along the way that you can just take the difference in electronegativity, take them one from the other, and then that will tell you what kind of bonds that we're working with. So I'll shut that down and go back then to just the last couple of slides. I think it's literally one or two. Okay. Oh yeah, so we literally have one slide left, and then what I'll do is I'm going to upload a couple of questions on a worksheet onto Moodle. We'll take maybe 10 minutes just to go through that, and we'll take 5-10 minutes at the end just to kind of go through your answers, make sure we're all on the right page, and we'll leave it there for this evening. So again, you'll hear me saying an awful lot of time that there's an exception to the rule. There's always exceptions to the rule. And it's kind of what I was talking about at the very start. We're not actually going to study these exceptions. It's just to kind of make you aware that these exceptions do exist, that it's not always as simple as kind of, oh, we'll just add one electron and satisfy the octet rule. So we had a first exception that it was hydrogen and helium. Okay, so they are stable having 2 electrons on their outermost shell and not 8, because the first electron shell can only hold 2 electrons at max. So there's 3 types of kind of ions or molecules that don't follow the octet rule. So we have ones that have an odd number of electrons. We have ions or molecules with less than an octet. So that's kind of what I was talking about there with our hydrogen and helium. And then we also have ions or molecules that have more than 8 valence electrons. So this is kind of going into our third and fourth energy level that can hold 18 plus electrons. Okay. Similar to what I said at the start, this is kind of looking to more towards the end of the periodic table where we have an increased number of electrons. Like I said last week, we're going to focus primarily on the first 20, if not 30 elements. So we're not going to go into these exceptions too much, just to make you aware that they do exist. Is everyone happy enough with that then, just before I stop the slide deck? Is there any bits you'd like me to go back over? Or have I melted your head enough for this evening? Okay, fair enough. So what I'll do is I'll stop sharing the screen and I will just pause the recording. All right, guys, if you're happy enough, then we'll start going through some of your answers for what you got, particularly for the electronegativity values. So if you have answered it, if there's a poll there on Zoom, you should be able to see. If you just want to click what you actually put in for each one, just as a couple of examples, and then we'll go through it. I'm just going to take a couple of them. I know there's a full table on the worksheet. I'll take a couple of examples that we have there and I'll go through them. Okay, so identifying the type of bonding that's in NaCl. All right. So for those who answered, they can see 2 answered that was ionic. That's correct. So by taking your electronegativity value of 0.93 for sodium away from your electronegativity value of 3.16 for chlorine, you should get an answer of 2.26 above the 1.8 cutoff for ionic, and therefore we have an ionic bond. So that's good. So for your second one then, so just taking the CaO as an example, so our calcium oxide. So calcium has an electronegativity value of 1. Our oxygen then has an electronegativity value of 3.44. So again, taking one from the other should get a value of 2.44, which is well above the cutoff of 1.8. So we also have an ionic bond there. So that's for your calcium oxide. Okay, so your CaO. So for your bonding in C6H12 oxygen or O22, okay? So this is an organic compound, okay? This is actually a non-polar covalent bond, okay? So this is a little bit different, is that so we have three elements to take into account here, all right? So we have your carbon is 2.55, your hydrogen is 2.20, and then we're also taking away oxygen, which is 3.44. So this is a little bit of an exception to the rule that this is incredibly non-polar. Okay, so we actually have an electronegativity difference there of minus 3.09 in total. So it's well below our non-polar cutoff of 0.4. Okay, these organic compounds, they tend to be a little bit different. So we just label them as non-polar covalent. Okay, because their electronegativity difference between them is very, 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 very small, almost in the negatives. So it's non-polar covalent. All right. So for those who answered that as polar covalent, just make sure that you now have that as non-polar covalent. So finally then, for just another example then, so your H2O, so your water. So we take account in the electronegativity difference between water, which is 2.20, and our oxygen of 3.44. That gives us a total electronegativity difference between those of 1.24. So again, well between our 0.4 and our 1.8. So you're right in saying that that is a polar covalent bond. Okay, so we have a difference in electronegativity of 1.24. So just to recap then, what you should have for that then is NaCl is ionic, CaO is ionic, the C6H12O22 is non-polar covalent, okay, due to a huge, like a very insignificant difference in electronegativity. And then your H2O or your water should be polar covalent. All right, is everyone happy enough with that?
You see, is it phosphorus with four oxygen? Is that a -3 charge in the notation?
Yes, that's a -3.
That won't make a difference for this, would it, to find the.
No, not as we're just looking at purely the element here. So you
Okay,
only
yeah,
calculate
grand.
difference electronegativity. So with that being said, I would assume that is ionic due to its electrostatic charge. Okay, so having a negative charge. But to answer your question, you'd only take into account your
Okay, yeah,
phosphorus and your oxygen
perfect.
there.
Yeah, thanks.
Is everyone else okay, guys? Does anyone have any other questions? Okay, perfect. So